talks lah. So before I let the speaker start his presentation, let me just introduce him lah. So for those who still don't know him, he's a very senior guy. He has been around for many years. Anyway, I will read a brief CV. Okay, professional, we call him professional geologist. You know, in geology, we have this PG or professional geologist, Devendran Arumugam. He's currently the SI manager in Gamuda. Of course, he worked on many projects under Gamuda. He obtained his BSc degree in actually physics, but majoring in geophysics. So that's the connection with geology, geophysics. BSc from University of Science, Malaysia. Didn't say what year. Devendran, what year was that?
1985.
1985. Okay, so roughly we know his age from that 1985. So he has 40 plus years of working experience, many projects, and focusing on geophysics applications in geotechnical engineering, tunneling, groundwater exploration, etc. Many kinds of projects. Like now he's working on the reclamation in Penang. He's a professional geologist at PGO, that's registered under the Board of Geologists. And he's a fellow of the Institute of Geology Malaysia, and he's also a life member of GSM. And he serves on the panel of industry experts at University Technology Petronas. Okay, with that brief introduction, I call upon Devendran to make your presentation. Yeah, Devendran.
Yes. Can you see the screen?
Yes.
Okay. So, good afternoon, friends and fellow geologists. So, this is a topic where is very difficult topic, cavity detection, especially in rock, in limestone, in KL. So I'm just going to share some experiences which I had mainly in the MRT project, MRT2 project. Okay. So we know, I think all geologists should know that the limestone outcrop, KL limestone outcrop, is in Batu Caves. I think that's the only place where you can see above ground. So you can see all the features of the KL limestone. So generally the contents will be general geology of KL, extent of KL limestone, the karst features and geological conceptual model, choice of geophysical methods, geophysical applications, and supporting software. Now, because this is a very difficult investigation, so we need to understand what is the karst features, and we also need to have a conceptual model. This is important to design the geophysical survey. Okay, and together with that, after processing the geophysical data, you also need some supporting software to visualize and to correlate to get the geotechnical industry to understand what we have actually done. So this is the geotechnical map of Kuala Lumpur. As you can see, the color in beige is mainly the Kenny Hill. The other one, the blue, is the limestone. So we can see that if you see this is the MRT2 alignment, the tunnel alignment. So a lot of the tunnel alignment actually traverses through the limestone, KL limestone. Okay, and we also have a lot of issues at the contact between the KL limestone and the Kenny Hill. Okay, this is also something which we have to keep in mind when we are doing the investigation. Now, this conceptual model, so this is an example of a conceptual model. This was used in the groundwater project in Batang Padang in Perak. Okay, so the conceptual model, this model came about. Actually, it's not easy to come out with this model because even though we have a lot of geology maps and all that literature, but it was actually through literature survey, field mapping, and preliminary investigations, which we came out to understand which of the lithology actually contains the water. So to build this model, you need hydrogeologists, geologists, geophysicists. So here we have the one in blue is graphitic schist, and the one in red is the quartz mica schist. So the quartz mica schist contains the water. Somehow the graphitic schist doesn't contain. So we have to find the fractures within the quartz mica schist. So we made this conceptual model. So we find that we have to do a geophysical investigation across the two lithology first, and then find the do another investigation only on the quartz mica schist. So if you look at this diagram here, the R1 line shows the low resistivity, which is the quartz mica schist, sorry, the graphitic schist, and the high resistivity is the quartz mica schist. So after finding out this, you map maybe two, three lines, then you lay your investigation along the high resistivity, and this is what we get. So with the help of this geology and the quartz mica schist, I mean the conceptual model, we can actually map quite well. So we can see the contact zone between the graphitic schist and the quartz mica schist. And within the quartz mica schist, we can see lower resistivity and high resistivity. The low resistivity areas are the fractures. Even though the resistivity is about 800 ohmmeter, it contains the water. We did downhole logging, and we found that actually it is about 800 to 1000 ohmmeter, not as what we always think that blue zone with 10 or 60 ohmmeter, something like that, contains the water. But this is why we need this conceptual model. So along the MRT2 alignment, we have this MRT2 alignment. We can see a number of stations are all in the KL limestone. We have some in Kenny Hill, and near the Central West Station, actually there is some granite. Okay, so when we study all this, initially we had preliminary boreholes, and then because we don't have outcrops, so it is an urban area, so we have to depend on literature and boreholes to map and get these soil profiles. So as we were doing the work, when the tunnel boring machine is going to pass through, we need to know the geology, we need to know where the weak zones are, the fracture zones, and the cavities. So we built up a conceptual model, and I think Mr. Tan Boon Kong was involved in this also. He helped us build the geological model. And this is the typical cast. So in Malaysia, it's extreme cast. So we have all those cavities and sinkhole, buried sinkholes, pinnacles, troughs, all sorts of features here. And all these in KL, most of the area, all these features are below ground. Okay. So this is taken from Boon Kong's paper. We can see that from all the investigations, he has actually mapped the shape of the limestone rock, and this is the overhang with maybe probably sinkhole area here. So we can see that it is highly variable. It's not easy to build a geological model. Okay, and here we see that at the contact zone where we have a limestone, which is very close to, say, Kenny Hill, then we also have slum zone. So SPT 0. But usually these are all very deep, too deep for the geophysical investigation. So these type of zones, we have to use boreholes. This is taken from one of after NEO, 1998. So I think the engineers were having a lot of problems in the what do you call that, pile foundations in limestone. So you can see their conceptual thing is if you have overhang, probably the pile can stand there. If you have a very steep slope, then when you drive the pile actually bends or breaks. Okay, so uh, you need a lot of what do you call it, detailed understanding of the limestone to get to design these pile foundations. So if you put a geophysical line here across all these, can we map all these features? So that is our question. So this is some of the features which we encountered while we were doing the construction in MRT2. This is in Chan Shaolin Station, very deep down, maybe about 20 meters down, 30 meters down. So you can see the features. So there are a lot of solution channels and cavities uh, in the limestone. So, but above, the ground is quite stable. But when you dig down, then you see all these features. This is the tunnel. This is the tunnel. And you can see just beside the tunnel, we have a deep cave. So, and here some solution channels. So the engineers will design this. Either they use rock bolts or graniting with reinforcement to protect these features. You can't go and fill up these features. So you got to just protect down there. And then later on, we will build a wall. So this is a twin tunnel. When it came out here, you can see these small fractures. So a small cavity, actually, if there is heavy rain or a lot of water ingress, then water will be actually coming out very fast here. And that will be a hindrance to the construction. So from Waltham, what he said that whether a particular geophysical method is inherently capable of detecting a change in physical property is dependent on required depth of penetration to the ground. Usually, as you go deeper, surface methods, the what do you call this, resolution drops. Okay, then vertical and horizontal resolution required for the anticipated targets. Contrast in physical properties between the targets and its surroundings. Signal to noise ratio for the physical property being measured. Because geophysics when you use physics, you need instruments. And instruments, the way they operate is you need sensitive enough instruments to detect the ground response. So the signal which comes out can be contaminated by noise. So example, if you're doing seismic, then any vibrations in the ground, car passing, vehicle passing, or wind noise and all that can disturb. So the signal to noise ratio will decrease. So you want a higher signal to noise ratio. In resistivity, the signal to noise ratio is the ability to detect the current which you injected, the response from that. So this is taken from the American Society of Testing Materials guideline. So if we look at voids and sinkholes, then what are the best methods? So refraction for seismic refraction and reflection is considered secondary. MASW is primary, but this is also limited depth, depends on the energy strength and the geophone spacing. Resistivity the best resistivity method would be coupled resistivity, but most of our electrodes are all steel electrodes planted, so it's actually DC resistivity. So this is not recommended in this table, but we all use this method. Now, mainly this method can be used if you are very careful with the steel electrodes. Okay, IP is another one, induced polarization, uh, spontaneous potential, which is uh, what do you call it? Very sensitive to water bearing. If you have water, you get variations in the potential. Um, the ground penetrating radar and gravity method actually stands out, but GPR is limited, has limited penetration. So to get even for above 3 to 4 meters is difficult. So this is the resistivity method. So we have this is ABAM and this is SuperSting. There are also other brands. We have basically we have 4 electrodes. A and B are the current electrodes where you drive the current through. So these are the red ones are the current lines, and that will induce a potential field. So the M and N will measure the potential field. Okay. So in this type of instruments, we have got many electrodes, multi-electrodes, and it will automatically switch and take readings. So example, electrode 1, 2, 3, 4. So it will use this A and B. 1 is A, and 4 is B, and 2 and 3 becomes M and N. Then it will switch. So that is data point number 1. So for data point number 2, it will switch electrodes and so forth. Now this one is from Loke's notes, Dr. Loke. He was a lecturer in USM. Now he's an independent consultant. He wrote the world famous software REST2D and REST3D inverse. So you can see that this table, the geometric factor. So geometric factor is inversely proportional to signal strength. So whatever arrays you use, you have to find the smallest uh, geometric factor. Then you will get a high signal strength. So if you use dipole, but if you use, say, n equals 8, then you've got a high geometric factor. Your signals, which you measure, are very weak. So you might get very noisy data. And this is also after look. You can see that if the cavity is infilled with clay, then you are looking at resistivities between 1 and 100 ohm meter. For limestone, you're looking at 100 to maybe almost 10,000. Okay, so very high resistivity with low resistivity inside the high resistivity rock. That will give you a good contrast to use resistivity. This is sensitivity. So if you're really designing resistivity surveys, then you would want to look at different arrays have got different sensitivity diagrams, functions. So example here, Venus Lumberger, you have got at n equals to 1, it's almost horizontal. But as it gets n equals to 2, that means deeper, it will be more, you have more vertical sensitivity. Dipole, at the ends, you get more vertical. As you get deeper, you get between the current electrodes and potential electrodes, you can resolve the vertical structures. So this is something which I think only a geophysicist, you must be really trained in geophysics to look at this to design your array. So this is an example of 2D resistivity along the smart tunnel. We had to map the cast features. Smart tunnel is a bit difficult because the tunnel diameter was about 13.2 meters, and it had only one tunnel diameter cover. That means you're tunneling very shallow. Just about 13 meters below is your tunnel, a huge tunnel. So when you disturb the ground with uh, thin cover, then you can you can lower down the water table, you can have sinkholes, you can have depressions and so forth. So the challenge was how to detect all these weak zones using a method. A lot of methods were tried: microgravity, resistivity, seismic. Resistivity proved one of the most successful method. The challenges in a built-up area is usually you don't have in line length, sufficient line length, because you need a straight line. So you don't have enough straight line. Surfaces are paved, so current cannot pass through. So you have very high resistivity, resistive ground. You got underground utilities. All these underground, what do you call that, cables, electric cables will induce spurious current into the system. Okay. Grouted structures, that means you've got piles, you've got buildings, you've got, in fact, if you've got freshly grouted area, it will disturb the electrical signals. Okay. Effect of 3D geological structures on 2D. So that means you got a straight line doing 2D resistivity, but you've got a structure which is adjacent. That means on the side of the line, if it is a low resistivity area, the current will tend to pass through that low resistivity zone on the side rather than passing through along the line. So this can complicate the issue of resistivity. Okay. Um, Urban data, very complex data processing, and it's a very steep learning curve, even for the most experienced guys. So it took a lot of time to understand how the ground behaves to resistivity. Data processing interpretation needs trained geophysicists. The advantage, good resistivity contrast between competent limestone and fractures and cavities, good success in detecting cavity zones. When combined with another geophysical technique, highly successful in detecting weak zones. So if you look at the site here, we found that from the experience of running almost, I think about 7 or 8 kilometers of along the alignment, we found that paved surfaces are about 500 to 1,000 ohmmeter. Competent limestone was about 100 to about 500 ohmmeter. And the weak zones were about 20 to 60. Okay. So this is what we need to look for in the resistivity sections. The other method which can help is MASW, multi-channel analysis of surface waves. This is actually now getting very popular in around the world. Uh, a lot of people are using this method. Mainly, the challenges is high ambient noise, mainly have to be done at night, limited space, obstruction by build-up structures, non-homogeneous subsurface, tedious data acquisition because you need to keep on moving the array many times, data processing and interpretation. Advantage, high resolution, good method for detecting shallow voids, fracture zones, highly successful when combined with another method such as electrical resistivity or microgravity. Okay, so this is one of the figures we were doing in MRT project. We lay the geophones here and we hammer on one side. Then you have to move the whole array. So this is something like this. This vehicle is pulling the array and then you strike. Then you move next station and you move the source by similar amount and you strike. So then you combine everything and get a map. So this is a S-wave velocity map. you get the shear wave from MSW, and this relates to the stiffness of the soil. Okay, this was in MRT2. We combined we combined MSW and 2D resistivity for risk assessment at mixed phase. So what we get is when we have Kenny Hill and limestone contacts, we can get a lot of uh, features there, weak zones or highly weathered or even slum zones. Okay, so this is the result of that. So the top one shows the MASW, and the bottom one shows the resistivity. When you one look at it, it's very difficult. If even if you had only the MASW result, also you can say that there are some weak zones, but it doesn't tell anything really more than that. But when you combine with ERT, here you have low resistivity, and that also corresponds to the low MASW, and that actually was a weak zone here. Okay. And similarly here, this was also a possible weak zone. So we tell the engineers, the tunnel engineers, so this is the tunnel alignment. We can see that this zone is very close to the tunnel alignment. So what they will do is they will go and pre-treat this area, investigate and pre-treat, maybe by grouting. This is looks very, very complex. This is a resistivity line. We have 3 lines. This was in SMART. So we have 3 lines spaced out at 10-meter spacing, 10-meter interval. That means each line is spaced out at 10 meters. So from this legend, we can see that the competent limestone is around the yellow to light green. So the yellow to light green and above is all competent limestone. So initially we were looking for weak zones. So those blue zones, they are the weak zones. But later on, they also found that this resistivity diagram was also useful for intervention. Intervention of the TBM. That means when the TBM moves along the alignment, then they have to, every maybe 250 meters, they have to stop, and the cutter head, they have to go in front of the cutter head and inspect for wear and tear. But when you stop, if the limestone is very fractured, then you get water ingress. So you have to, pressurize the chamber in front. So it is a big task. So later on, they found that actually using the resistivity, they shift the intervention block to where is really competent, because when you're passing this area, there is hardly any fractures. So you don't need this pressurized chamber. You can actually go in and work safely. So that was the advantage of resistivity, which which we discovered during the course of the work. So this is some of the photographs. So you can see the conditions. It's not that easy to work in. This paved surface, you have to drill through. After a lot of experiments, we found that actually if your electrode has got contact with the side of the pavement, that is more important than actually having contact at the tip of the electrode. So the side of the electrode has got more surface area, then it is easier to you got a better chance of passing the current through the pavement. Okay, so these are some of the areas where we have to plant the electrodes. These are the road protections, and this is one typical section where you can see the pinnacle here, and the trough and the pinnacle, and some boreholes which try to correlate. So this type of shallow areas, these are quite risky to the tunneling. The tunnel actually passes very close to the weak zones. So a lot of grout treatment was done to these areas. The other method we use is gravity survey. So gravity survey so far has been quite successful in MRT2. Okay, uh, we actually applied it first at in MRT1 in Maluri station. So we actually the gravity survey helped detect some of the anomalies. Okay, the challenges is it takes long for the mass to stabilize. You know, the gravity meter has got a small mass inside, and this mass is attracted to the earth. So if you have a high density material, then it will be attracted more. If you have a low density, it will be attracted less. So that's what we are looking for. But if you got vehicles passing by in the urban areas, this mass will take some time to stabilize. So it it may take longer. Okay, passing vehicles can affect the readings. Corrections have to be made for effects from large buildings or drains. If you've got a large building, that can have a mass which can affect the uh, gravity reading. It's very sensitive to ambient vibrations, complex data processing, steep learning curve, data processing interpretation needs trained geophysicists. This one really you need a very experienced geophysicist to get uh, useful data, useful interpretation. Okay. Advantage is portable equipment is very portable, easily transported, sensitive to small changes in material density. So you can have very small changes in the material density. It can detect, can cover large areas with low cost. But one thing I have to add in is the cost of the equipment is quite a costly equipment. Okay, so it can sorry it can uh, it can cost about 500,000 ringgit for this small equipment. Okay, so the investment is high for the contractor. So the microgravity, yeah, the precision is 0.01 milligel. Idea is 1 gal is 1 cm per second squared. So, and that means our G, as we know, 9.81 is 900, approximately 980 gals. So you can imagine what kind of sensitive equipment is this. Okay, so this is a small illustration of the gravity. So if you have a small, low gravity material in between the granite, let's say, and if you profile along this granite, this geology, where you have the low density, you will see a dip in the gravity values. Okay, but if this was homogeneous, all of the same material, let's say 2.6 gram per cm squared, as cm cube, then you will just get a straight line, you know. So this one is higher density, so you will get a higher peak. If you have a fault, you will get an inflection type of curve. The limitation, example here, you have got a body, so you get the anomaly here like this. It can mean that it is a very deep-seated, high-density body, or it can be, a bit moderately seated, but a bit elongated body, or a very thin body, but higher, very high density. So all three will give this same anomaly. So here you have a limitation. So because of this limitation, what happens is you need a lot of experience and experienced guys to actually look at this. So looking at these cast features, how do you actually design a geophysical survey? It's quite a headache, you know. You really have to think hard and uh, uh, to determine what method you are going to use. You can see some are very large. So this was the Chan Shaolin station. So you can see that how we design is because the features are not kind of linear or the thing, it is, holes everywhere or cavities or low density. Sometimes you don't get caves. Sometimes you just get very weathered type of material inside there. Okay. So the best way of doing this was to do gravity measurements in a grid form. Okay. So after discussing with this was done by submap geophysical. So we discussed with him, and then we came out with this 5 meter grid station. So a total of 999 gravity stations were measured. Later on, this is the LRT Chan Shaolin. We had some depressions there. So we extended the gravity measurements here to also measure and see what are the features we can detect. So from the features, we see the residual anomaly map here. We can see a deep trough, low density, okay? And we can see that the trough is somewhat, what do you call that, contained within this valley. So beyond here, the gravity values increase. Beyond here, also the gravity values tend to increase. So this is the outline of the station, the proposed station. This is the existing LRT station. So we can see that this can be attributed to shallow bedrock, and deep trough. But this corner had low density. Here we have some low density areas. So these are all, when we excavate, we can actually see what was inside there. Then we did, this is the bouquet map, and then from the residue, this is the residual map. So residual map is basically, bouquet map includes the local changes and the regional changes. So you minus off the regional change, you can get the residual map. And from the residual map, example here, A, B, and C, we can do some modeling along the lines. Now, from the gravity map, you can have an idea of how the gravity values change, but you can't actually get a geological model out of it. You just have to depend on uh, gravity modeling. So it's a geophysical modeling. That is why you need people with experience to do this type of modeling. Okay, so these were the lines A, B, and C. So we can see that the blue ones are the observed values, and after you do the modeling, you will get the red ones, the red line. When it fits well, then that is the model here. So you keep on changing this model, either the shape or the density, until you get this fitting. Now this density 1.8 we derive from our soil investigation. So the limestone, I think, is quite established. So we give the sediment velocity, the densities, and then the geophysicist does the modeling. So from this model, so we can see here, we had a lot of rock probes. All these small dots are rock probes. And then we had some boreholes. We also did some downhole logging. We used these ALT downhole logger, televiewer. We could map the main directions of the fractures. And then you can see that this area where the valley is, we had to do a lot of ground treatment, okay? The advantage of the gravity survey is, at first, the region looks quite large. But after the modeling and when we include, we find that actually the region is much smaller. Okay. So this is the advantage of the gravity. And it also gave us indications that these areas are also can have uh, solution features. So this, if you plot correlate these features, we can see that this was a big valley. So we did some ground treatment. These are rock anchors in the valley. The limestone actually goes down like that, and it correlates to this very low density. Okay, this area was highly weathered. You can see even these small ones are huge. Okay, so this all this comes out quite clearly and correlates well. So MRT2 gave us a very good project, a very good platform to test this microgravity and the geological features, because without excavation we wouldn't have known what was under the ground. So we use some of the tools. This was using the Voxler. So this is the Bouguer anomaly map, and this is the bedrock map. You create from all the rock probes, boreholes, and gravity. And if you look at this one, we zoom into this area where the valley is. There was a lot of grouting, so we also plotted the grouting. So gives us a very good understanding of how to plan the mitigation and the construction. Okay, you can see this valley. There was a lot of grouting. This was in the Maluri station. So the houses, while the excavation of the station is nearby, the houses had some cracks and some settlement. But unfortunately, we couldn't bring in any SI machine to this area because if you look at the lots, all these lots, they're all side by side. No, so you could not actually bring in the SI machines there. So we decided we will use gravity. So if you look at these stations, these squares, the black squares are the gravity stations. Okay. All these inside, some of the places we can bring in and take measurements, some we cannot because these are all houses. These red crosses are some of the additional gravity measurements we made during the course of this. Now, this one, this map is compiled from boreholes, secant bore piles, and king posts. So we put in all those, we have information of the boreholes and then all the bedrock topography. So we created a map. But when we analyzed the Bouguer anomaly map, there was a large similarity between these two. Okay, you can see that these are very steep contours here, the gravity contours, coincides with this steep bedrock topography. High gravity values, shallow bedrock here. These lower values were lower bedrock topography. You see, all this was coinciding. So now the issue was why the crack was happening. So did some processing, we got the residual map, and then did some modeling, and then we found some model. Now this is just a geophysical model, so it does not mean that geologically it's correct, but we can't even investigate because we can't take a SI machine there. So we did this model and included into the bedrock map, and we found that there were two areas here where there was low gravity, low topography. Okay, on the 3D, we can see that. And that means that the house is on very sloping topography, bedrock topography. And there was also groundwater drawdown in some construction beyond here. So that caused the settlement over these houses. And that were the houses which were having the cracks. So this is where uh, gravity helped us to detect in the absence of boreholes. Okay. And the other one, another example is Sungai Besi crossing. Okay, this is the tunnel alignment, which is from Bandar Tun Razak is going towards Chan Shaolin. This is going to Chan Shaolin. This is from Bandar Tun Razak. This is the Jalan Sungai Besi. That's 13 lanes it's crossing. Okay. There's no way we can go and do boreholes there. We can't stop the traffic. Uh, DBKL didn't allow us to do any investigation on the road, but we have got 2 tunnels to bore through. The client MRT Corp was very worried that you could cause sinkholes there. So we decided that we'll do the microgravity. So these are the, what do you call it, stations. We did 5 meter spacing. These are the lanes. And the anomaly maps we got, okay, Bouguer anomaly map and the residual map. So the residual map shows that there are 2 anomalies here which are concerned, whether they are in the tunnel horizon or not. So if it is there, then it can be a risk to the tunneling. So there could be a risk to settlement. So we did some modeling of those, you know, there were 2 models we did along AA dash and BB dash. And these were the 2 models we got. And then we incorporate the models to some of whatever existing boreholes we had by the side of the highway. Then we found that these anomalies were up to here. Okay, the rest of it was generally benign. The bedrock doesn't really extend. I mean, the anomalies doesn't really extend to the tunnel horizon. So what we did was we did incline borehole by the side of the road. We inclined it and drilled to intersect the tunnel horizon just by the side of the anomalies which we detected in the microgravity. We found that there was no the bedrock was competent all the way. So TBM crossed, I mean, confidently crossed with this data, confidently crossed the Jalan Sungai Besi without any incident. Okay, these are some of the gravity measurements being taken. We have to be, you really have to plan this meticulous planning, night work, teamwork, because each station you also have to take the level X, Y, and Z. So there are so many stations, we have to carefully label them. You can't go and paint on the road. So all this has to be taken into account and then completed within 3 days of data acquisition, 3 nights. Very well planned and done by our subcon. Okay. So next one is shallow sinkholes. These are sinkholes which are not in the rock, but below, say, below concrete slab or something like that. So this is one of the diagram which I like actually. Sinkholes in taken from this DCNR Commonwealth of Pennsylvania. So if you have a bathtub and then you have a drain and you have water dripping, it goes inside and this cavity starts forming. There's washout here and cavity starts forming here. So when it is thin enough, then it have a depression. So this model can be used to actually run for shallow, what do you call it, detection using GPR. So this was also in the Jalan Sungai Besi. What we do is we monitor any, we keep on monitoring daily until the TBM crosses. So we just compare the anomalies to see any minute changes. If any changes, then we will inform the grouting team and they will go and investigate. Okay, of course, GPR, the challenges is underground utilities, signals interfere with target signals, high intensity reflections from metallic objects, manhole covers, steel plates, okay, even water, pool of water can disturb the signals. Some of the build-up areas is difficult to do, run a GPR. Limited penetration mainly in Malaysia because of shallow water table, clay soils, cemented pavement with steel reinforcement. Data processing and interpretation, I think it's not so straightforward as utility detection. Okay, utility detection, you look for parabolas, but for other things, you really need to do some geophysical processing. Okay. Advantage is a non-invasive method, no need digging or excavation. Real-time data pre-processing can be done on site. High resolution, high precision. GPR is very high resolution. Can be used to monitor shallow subsurface movements. Minimal obstruction on daily activities. Extremely portable and quick to deploy. So this was near Jalan Ipoh, where the TBM was moving. While it was drilling, while it was excavating, which is quite deep down, but it was already coming up. Let's say, I think maybe in this area, the tunnel alignment was about 10 to 20 meters deep. But sometimes you can see that it has disturbed the ground and the bentonite starts leaking. So this is where we are worried. So this is before the TBM is coming. So we scanned here, okay. Then now the TBM cutter head is here. We can see some changes. You see, this change is very obvious here. And here you can see something happening in this area. This is actually the bentonite, which is leaking out, which is coming out from the TBM. It has slowly come out to the sea. Because bentonite is clay, so you can have some contrast in the GPR signals. So when we have this type of detection, then we tell the mitigation crew, we call them the bull gang. So the bull gang will go and watch out for any leakages, and maybe they will do some grouting or mitigation measures. This was in what do you call this? In MRT1 in Jari Bate. So the Jari Bate, there is a Bate, what do you call, tourism area. So they have a floor slab, and the TBM was passing nearby, and we had depressions. In fact, we had the floor slab suspended. So we did some GPR. What we did was, you can see here all these lines, okay, A to K and 1 to 14. We closely spaced GPR, we scan them, and then looking at these anomalies. So this is like, this is a void, okay? These are all voids. You see signals which high intensity. And then, what do you call it? We look at where we study, how the signals look like. This is previous grouting. You can see here, this type of ringing is possibly caused by air, and then there's a small depression there. This is the original ground, and then what we did was, all the lines we put it in pseudo 3D. Okay, when we put in the pseudo 3D, we can see high intensity concentrated on this area. Okay, these are the low intensity. So this high intensity is where the signals ring because of the air void. So then we did some grouting. These are the black ones are all the grout holes. Okay. But to compare this one, you got to normalize the signals, all the signals to the same parameters. Uh, this is to show what do you call it, gravity modeling, how actually models can work. Of course, you do the gravity, then we did some modeling. These are the lines where we wanted to do the modeling. And we had some boreholes. This was quite lucky. We had some boreholes also. So these colorful ones is the residual anomaly map superimposed with the boreholes modeled in AutoCAD 3D. So we can see this in 3D format. Okay. And then these were the gravity models, geophysical models. But if you see, when you do the geophysical models, the baseline is the top of the base, which is shown as 0, is actually the top of the bedrock. It is not the top of the topo. It is top of the bedrock. So it is always at the top of the bedrock. And this is the shape of the anomaly which you model. But if you have some values for the bedrock level, then you can actually get a section, okay, a bedrock cross section with the ground surface and the overburden. So example, this A is this one. So on the geophysical model, it looks like this. In the real one, it looks like this. Okay, this one translates to this. So how we get this is because we have some bedrock values. So you can redistribute the bedrock levels here. Okay. So this is one advantage of the gravity. It doesn't need to have totally, of course, the gravity model gives you some idea, but it can also tell you better looking picture if you have some borehole data. Another method is using the crosshole tomography, seismic crosshole tomography. We did this in Conley Station. Very interesting this thing because we have these two boreholes, PB7 and PB6. So we shoot across. In one side we put the boreholes, hydrophones. Another one we put the source. We shoot. We shoot at many depths, receive at many depths too, and then we can see very clearly. So this is, we take the contour. That is the top of the bedrock, and this is a cavity here. Later on, we did a borehole to confirm this. It was quite good matching. Okay. And here we can see a low velocity in the bore log. It was logged as water loss. Okay. So supporting softwares, we got, these are all the softwares we usually use to enhance the presentations or the computations also. So we got ACAD, Voxler, Surfer, Rockworks, and of course the Excel, which is very useful. This is using the AutoCAD and data from GPS. We can plot the lines of the resistivity. This was for a groundwater project. So we have a river. They wanted to take riverbank filtration. So this is the resistivity and IP sections. We put it. This one was using Rockworks, Surfer, and we can get this. And we found that the best water zone was around here, the higher resistivity. Okay, so high resistivity is it means that high resistivity is the fresh water. Fresh water has a higher resistivity than maybe muddy water. So summary, the challenges Usually irregular shape and size of cavities. So very unpredictable, very difficult to get that. Variable target depths. In urban and suburban regions, geophysical surveys are largely prone to cultural man-made noise, natural noise, complex geological conditions, surface heterogeneity. That means the soil and the surface also is not very homogeneous, tends to distort the geophysical signals. Non-uniqueness in non-unique solutions. That means that when you measure the data, when you do the inversion, you can get a model. But for the same set of data, you can get many solutions. So which is the best solution? I think this one, the geophysicist has to decide. Okay. Limited applications of each geophysical technique. So sometimes you have to see which is the best. Many times, small projects, client does not have enough budget, but combination is better. Um, Ambient soil conditions, clay, shallow water, common limit to, say for GPR. It is dependent on trained personnel. Geophysical operators, data processors, and interpreters need to be highly skilled and properly trained. Okay. Cost implications. Geophysical surveys can be expensive on a small scale project unless other site investigations cannot be carried out. Practicality on one of the major limitations of the geophysical method is lack of space. In densely populated urban areas, it may not be possible to carry out surface geophysics. So you might need borehole geophysics. So even borehole geophysics, you have got cross hole, you have got televiewer, you have got downhole cameras, you've got many tools, resistivity, IP. So there are many methods you can use. I think um, this geophysical methods are getting more popular nowadays. Okay, to achieve the desired results, you need good knowledge of geology of the survey data. So you've got to do some literature survey, some background survey, read up on, get go to the library, get some data on the surrounding geology, sound knowledge of the geophysical method to be used. Okay. Survey carried out by competent geophysicists familiar with the technique in data processing. This is very important. And you also must know what is good, moderate, and bad data. Sometimes however you try, you might not get good signals in seismic. So you have to decide when to stop, when to, what is the next mitigation and so forth. Competent in using relevant geophysical software. You got to be focused on the survey objective and able to defend the findings to the engineering client. Okay. Soft skills using visualization software will be useful. So with that, I think I'll be ending the session. I think just nice, 1 hour. So I thank GSM, Gamuda Engineering PSR, which is Penang Sea Reclamation, MMC Gamuda Tunneling. Now, just one final slide. This is the project we are working on. This is the conceptual model. This is Penang Island. This is Batu Maung area. This is the island being reclaimed. So in future, we will have a, what do you call that, a link from the second bridge to this island. We have this red one is the LRT, which is coming to the island. And we have this from Penang International Airport, we have a road which will be linking, and there'll be a lot of development here. So we are sort of around this area now, reclaiming, coming to the we need to complete the depot. Okay. So with that, thank you very much. This is the Chan Shaolin station. When this is the valley, This is all after the wall has been completed. So thank you all for listening. And if you got any questions.
Yeah, thanks, Devendran, for a very interesting talk. Covers a lot of grounds, lah, all kinds of
Yes.
methods and some very good case studies. So okay, we have it's good timing also, about 1 hour. So we have about half an hour, lah, 30 minutes for Q&A. So I open to the floor, lah, to ask questions. If you can direct your questions directly to the speaker, no need to use a chat. Just speak up, lah, speak up. Okay, who wants to start ball rolling? Question. I see some familiar names, but if you can ask directly, lah, no need to wait for me to call you. Okay.
Hi, hello.
Yeah.
Yes.
This is Hafizi. I have a question for Mr. Devendran.
Yes.
So
Hafizi.
nowadays, there's a lot of geophysical survey needed to be done in urban or congested area. Congested area like a small factory area for groundwater exploration. So, in your experience, what kind of geophysical method suitable for this kind of situation? Thank you very much.
I think for groundwater mainly is resistivity. I think that's what they are looking for. But to interpret, with confidence, you really need to see whether you have enough space. Sometimes when you say factory lock, you might not get the depth if you're doing the surface geophysics. So you may have to do some borehole geophysics if you are doing in a small area. So you can have two boreholes and then do some cross-hole seismic or resistivity. You can even do cross-hole resistivity and IP if it is in limestone area. So it all really depends on the space and the geology of that area. Yeah, I think unless you really see it, you got to visit the site visit and put in some geology in that and try to find out. Yeah. I hope that answers your question.
Thank you, Mr. Dev.
Okay. Easy.
Next.
I don't know whether you can hear me.
Yeah.
Yes,
Okay.
yes. Can.
My audio is not very good. Thank you very much, Dr. Devendran, Mr. Devendran. Very nice
Yes.
talk.
Okay,
I was
thanks.
just wondering, because you mentioned it yourself that moisture was a small challenge for your resistivity methods. So I think, and you have also illustrated in your talk. Can you hear me?
Yeah,
Can you
yeah.
hear me?
Yes.
In your talk that in the area that you surveyed, there is variable moisture content. So a simple question is, how did you compensate for these moisture variations in terms of your 2D resistivity? And in upscaling the data to the size of the project area, how much of compensation did you take into account in terms of negating that variability so that you have an overall good assessment of the project? I hope you can hear what I said.
Yeah, yeah. Okay.
Thank you.
I think for the resistivity survey in the urban area, especially for the smart project, the main issue was actually getting good signals. Okay. So I actually worked with Dr. Lok he designed the parameters, I mean the array. We use a mixed array. Make sure that we use all four electrodes. That means we were using Schlumberger plus dipole. And that was for the array to ensure that good signal to noise ratio. When it comes to the practical part, it was planting the electrodes. That was the toughest. So we went through about 2 months of experimentation, trying to find what is the best method of planting the electrodes. So there are many ways of planting the electrodes. The main thing is to reduce the resistance around the electrode. So you can either use salt water or some clay inside there. Get the contact very good and make, before starting the data acquisition, make measurements of the resistance between all the electrodes. So because in urban area, you have a lot of noise. You can have a lot of issues with cables, underground pipes. These are even a higher noise than, let's say, because of moisture or something like that. So at the end of the day, getting the good data is very important. Now, the next thing we learned from experience was, even if with RMS error between 10 and 20%, we could get useful results. But you need a lot of correlation. You need to know where your utilities are and then make corrections for that. So when you're interpreting, you need some background information. The client was kind enough to actually give us a lot of borehole info so we could correlate. And I think overlaying this with the tunnel alignment and the other important thing is actually the ground survey. When we do the ground survey, we make sure that we are doing within the engineering survey standards. So that is the third class survey. Yeah.
Thank you, Mr. Devendran. Thank you.
Okay. Thanks.
Okay. Next question. Actually, the previous question he asked about how you compensate for the variation in water content in the soil, for example, right? Is there a way you were saying it is affected by water content, variation in water content of the soil, I guess.
For resistivity survey, is not really, water content doesn't really affect. Of course, when you have moisture, you tend to get, together with all the ions, you tend to get lower resistivity, right? So that you don't really compensate for that water. Maybe GPR, you need to do some processing. You can actually do some corrections for water moisture content.
Okay. Yeah. Next question. We still have quite a bit of time.
Can I throw one more question in?
Yeah, sure.
Yeah,
Go ahead.
Mr. Devendran, you mentioned that the seismic surveys were anything but perfect in your area. Now, coming a little bit from the oil and gas background, I noticed that this is a statement which is a bit, probably needs some explanation for especially students who are probably sitting in this arena today. In the oil and gas, we can go in quite deep under the sea and all. But when you're doing this seismic survey up to 6 to 8 kilometers, what were your major obstacles and for you to conclude that it was a bit difficult to interpret the seismic output that you had? Thank you.
Okay. In our case, we are only looking at below 30 meters, maybe 40 meters, below 40 meters at most. If we use, generally we use we do refraction, seismic refraction, not reflection. So because reflection becomes quite tedious and expensive for this type of survey. The other thing was, when we do refraction, where we have a lot of ambient noise. So that is one of the major problems. We have vehicle passing and vibrations. So that is one of the limiting factors. The other one is when you have shallow targets, the signals used to are quite distorted. So it's very difficult to pick the first arrivals. So unless we do reflection, then I think we have a better chance of getting good data. In this area, we could not, it was not practical to do reflection. So, but in MRT2, we tried some reflection, but it was S-wave reflection. There was some correlation in hydrothermal changed area in Sentul. There was some hydrothermal alteration in the granite, and that zone actually was shown quite well in the S-wave reflection survey. But other than that, we didn't really do extensive reflection.
Okay, thank you. But
Okay.
I think I have to give a hats off to Gamuda because you have shown clearly that you can use a series of methods, a hybrid as well as non-invasive methods to come about with a reasonable picture of your area. That is, I think, a very nice take-home message from your talk.
Yes.
I have to thank you for that. I think all students who are watching this would have learned tremendously from you. Thank you.
Yeah.
Have a nice day.
Okay, next is Dr. Gui still around? Dr. Gui, Junior, or maybe he has left. Dr. Gui, oh, I think he has left. Okay, how about Philip? Philip, you're still there, right? Any question from you? And I'm calling some of the consultants, the GMP guys. Philip. Okay, keeping quiet. Right then, open to the floor. How about our groundwater lady? Noor Shafina, you are still there, right? Dr. Noor Shafina? Your name is still there, but I'm not sure whether the person is still there.
One question.
Okay.
Can
Go
I
ahead.
question? I think we did a lot of study, right, for Kuala Lumpur for this project with some methods and methodology. Maybe different, but sometimes very similar. Do we have access to all those data? Or we kept in one centralized data center, that kind of thing. So hopefully one day if another company, another project wanted to use the data and make a comparison, so they have access and, when building up a new things from existing knowledge, maybe we can enhance the understanding and, understanding of the either geological, either structure, or those kind of thing, yeah? Building something on the previous knowledge and data. Do we have like centralized data collections or centralized center, or even it can be kept by IGM or GSM, for example? Thank you.
think, yes, thanks, Samsul. I think now at the moment, all the data belongs to MRT Corp. Okay. So if you want the data, you have to write into them. It will be easier for, I think, universities or, to write in to get the data for maybe research purpose. But for private, I'm not sure whether they will release the data or not. But you have to write into MRT Corp. Yeah.
I think it's private property, because you spend the money to collect the data, so that's why it belongs to the company lah. Whoever paid for the survey. But actually, for borehole data, there is actually a law that compels the contractors, borehole contractors, to submit the borehole data to GMG. So in GMG, you actually can get all the borehole data, even in private projects, MIT projects. But there's no law to compel geophysics data to be sent to GMG. Okay. Okay, Sid, I saw your comment in the chat. Sid Jinping, any question from you? He's a groundwater man. Yeah, Sid.
That's very good one, Dave.
Thanks.
Good talk. You have actually used geophysics very successfully, but then you have the privilege of using a combination of all kinds of methods. But I'm always keep looking for a cheap and effective way to look for groundwater.
Yes,
So
I know that.
I'm sure in your experience, you know, one of your target is actually to look for groundwater. So maybe out of all your experience, maybe something can come out of it lah. Some more, not say 100% kind of thing, but more effective than what we have been doing now, just using a simple resistivity. Maybe next time you can present a paper more specific to looking for groundwater. Thanks.
Yeah, I think maybe from my experience, I think I work with you, Sid. We worked together with the groundwater project. We did a lot of resistivity, but I think looking for groundwater is one of the toughest things. For me, understanding the hydrogeology and then trying to apply the geophysics is quite tough. Even now also it's quite tough. But there are some gadgets in the market, I know. They all claim that you just have to go and do a short line of 10 meters or 20 meters, and they can find wells which can drill up to 200 meters, and get a lot of yield. But I don't think so. It is really true. But other than that, I think so far for groundwater, resistivity seems to be the good one. But if you're looking for hard rock, it would be also useful to do some seismic to map the bedrock and then do the resistivity to get anomalies within the bedrock. So you can see the fractures or something.
Yeah, my concern is always a matter of cost.
Yeah.
The some companies are very reluctant to use geophysics. So you have to really find a cheap and effective way. In my experience, in fact, we did some work for the data center for the Chinese company. They are very disappointed with our geophysics. They say in China, their geophysics can penetrate up to 300 meters. So I don't really know what they do or how they do, but I'm hoping someday somebody will find out and get back from China.
I think what they mean is using MT, magnetotellurics. I think China is promoting MT now very aggressively. They have used that in ECRL. I think they mapped it quite well, the fracture in the granite, quite deep, and the TBM also managed to hit the fracture and water ingress quite badly, So they were delayed for, I think, 3 or 4 months. I think if you're looking at very deep, you got to use magnetotellurics.
Yeah, maybe you can share a paper on that.
Yeah, but I think in Malaysia, I don't think there is there's a company doing it. Maybe JMG has equipment. Maybe in future there'll be companies who will invest in MT because some of the even dam projects they are looking for quite deep structures.
But actually, as a side thing, don't know whether it's a joke or not. So the Chinese company finally brought in their team, and I have a chance to peep at what they do. And one of the things was they use a dipstick. Seriously.
So that is what you are doing at the Padang.
Thanks, Dave.
No, we tried that, but I still think that using our conventional geophysics still gives the best results. It's more scientific. It can be explained.
Yeah, it's always a matter of interpretation. That's the challenge.
Yeah.
Thank you.
You're welcome.
Just a comment for Sid. Sid, good thing not cheap, cheap thing not good. So have to remember
No. Chinese people will say cheap, good, and best.
Cheap thing can never be good, It costs money to do something good. Okay, we still have about 5 minutes. Can have 1 or 2 more questions. I was looking for Dr. Nur Shafina, groundwater lady. Are you still there, Shafina? The name is still there, right? Oh, but
Yeah, hello, Mr. Tan.
okay, yeah, yeah.
I lost my voice already.
You lost your voice. No, I can hear you clearly. Your voice is fine.
Yeah,
Groundwater, geophysics, groundwater.
yeah, but yeah, first of all, I would like to thank Mr. Devendran for the very interesting presentation. And just now he said that there is a promising if university, because I'm interested to study cars,
Yes.
hydrogeology, yeah, with the vast data and exploration and records like this and reports, I think it's possible for universities to delve further in a way to benefit in case there is you never know when it comes to groundwater. I mean, there is a good to study, yeah, the findings, uh the projects in cars. I think it's useful for to start with. I think that's the comment from me, Mr. Tan. Thank you.
Okay, yeah,
Doctor,
maybe that, yeah.
you
So,
can write to MRT Corp. I think they're quite helpful, in sharing the data for research. A
right.
number of universities have actually taken the data and done some research.
Okay, thank you,
Yeah.
Mr. Devendran.
Yes, welcome.
Yeah, just for information, Shafina is our new chairman or chairwoman, chairperson
Yeah.
for our working group on hydrogeology, GSM. Okay.
Congratulations, Doctor.
So hopefully she'll be more active in the society and organize more talks on groundwater. Okay, one or two more last questions. Still got 4 minutes. 5:26. My computer says. Any more questions from the floor? Philip has gone off with it. I called Philip just now, but he didn't respond. Okay, I have one or two short questions. Number one is limitation of depth lah. Like for your what's the maximum depth? 30 meters, 50 meters?
I think most of our surveys are within 30 meters.
30 meters. So anything below cannot detect lah.
It's not to say cannot.
Yeah.
Your cost will go up. You can do it, but the
Still
cost
can
will
do
go
it.
up.
Okay.
Can do.
Can
I
still
think
do up to
geophysics,
50 meters. 50
yeah,
meters I can.
oil companies are doing kilometers. So
No. I mean for engineering purpose.
yeah,
not
engineering usually cost effective is
Yeah.
about 30
meters.
meters. Yeah.
Okay, the other question, short one. If you have a stacked cavities, cavities at two levels, let's say one
Yeah.
at 10 meter and one at 20 meters cavities.
Yes. Yeah.
Does your geophysics show up two cavities or just one distorted cavity or something?
Gravity will have a tough time.
Any
Okay.
other method can pick up the stack
You
cavities?
you can do it. Maybe you can try resistivity.
You can
it
pick
can
up, say,
resolve.
one at 10 meters, another one at 30 meters.
Yeah.
I know we
You
can
can.
always do drilling lah. Borehole can always show that.
No, you can do resistivity because for the shallower one you use a smaller spacing nearer.
Yeah. Right.
Then you use a larger spacing for the deeper one.
Okay.
Yeah.
Right.
You can do that.
Okay. Last call. Anybody? We are quite close to 5:30. Last call. Anybody?
Yeah, I just want to add in that
Okay.
we also use borehole geophysics in the projects
Yeah.
in
Okay.
MRT. Actually, I think Rain from ALT, he's here. They supplied that equipment. It helped us a lot, and from that downhole camera, we also managed to do magnetic to detect pile length. So it was a offshoot from the original intended equipment function. You see, the function of the equipment is to look at the map the cavities or structure, but we also managed to look at the magnetic values. Used it in the pile detection. Very successful.
Yeah. Okay. So with that, I think we have one last function is to take a group photo for our newsletter. So can the audience turn on your camera, your video? Then we take one or two photos and group photos for the newsletter lah. Usual.